This section finishes up Chapter 4 and we'll be looking at complements and conditional probability. When finding the probability of some event occurring at least once, we should understand the following. At least one has the same meaning as one or more. The complement of getting at least one particular event is that you get no occurrences of that event. Finding the probability of getting at least one of some event. You can let A equal getting at least one of some event, and then the complement of A getting none of the event being considered, and find the probability of the complement of A, so the probability that the event A does not occur. And then you'll subtract the result from 1, so that means you're evaluating the expression that the probability at least once one occurrence of event A equals 1 minus the probability that no occurrences of event A happen. Here we have an example. Suppose that 55% of puppies from a certain dog breed are male. A sample of 3 puppies is randomly chosen. What is the probability at least one of these puppies is male? So we're going to take a look at this and how you would figure out that at least one of these puppies is male. So one way to approach this problem is to find all the combinations of genders that we can see for these 3 puppies. So that means you're looking at that sample space. So we would have male, 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 female, male, female, male, male, female, 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 male, male, female, female, male, female, male, female, and female, female, female. So these are all the possibilities of the 3 puppies being born. So which result meets the criteria at least one male? So if you're looking at least one male, you're actually looking at everything, right? Everything except female, 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 that all of them are born female. So there is a long way to find this. You would say the probability of male, 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 and then what that chance is. So it's 0.55 to the third. And then you would do the probability of male, male, female. So this is going to be that 0.55 times 0.55, and then the probability of a female is 0.45. And then you would keep going for all of those probabilities that had at least one male. That could be a very long process. And then once you would find all those probabilities and actually do the multiplication, then you would add them all together. But we have another way that we can do this. The simpler approach is to define the complement of at least one male, and that would be not at least one male, so no males. So that means we would be just looking at the probability of female, 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 and that would be 0.45 times 0.45 times 0.45. And if you put this in Excel, you would get 0.091125. Now, female, female, female is the only way to get not at least one male. Every other situation is at least one male. So that means that we actually can subtract the probability of female, female, female from 1. So to get the probability of at least one male, we can say 1 minus the probability of female, female, female. And 1 minus that probability of 0.091125. So we've got 1 minus 0.091125, and we would get 0.90875. And if you were to put this into a percentage, so I'm going to just come up here. This is approximately 90.9% of getting at least one male. Here we have an example. A study by Square Trade found that 6% of damaged iPads were damaged by backpacks or bags. If 20 damaged iPads are randomly selected, find the probability of getting at least one that was damaged in a bag or a backpack. Is the probability high enough so that we can be reasonably sure of getting at least one iPad damaged in a bag or backpack? So let's take a look at the work for this. The first thing we're going to do is say we're going to let A be at least one of the 20 damaged iPads was damaged in a bag or a backpack. Our second step is to identify the event that is the complement of A. Okay, so a complement is not getting at least one iPad damaged in a bag or backpack among the 20. So, and then we have all 20 iPads damaged in a way other than a bag or backpack. So let's look at this solution. If we're going to find the probability of the complement of evaluating the probability of a complement, okay, so the probability of a complement. Now, this is the probability that all 20 iPads are damaged in a way other than a bag or backpack. Okay, so we know that the probability of getting damaged in a bag or a backpack, it told us that is 6%. Okay, so I'm going to come over here and just make some notes for us. So we know the probability of getting damaged is 6% or 0.06. So then the probability of not getting damaged in a bag or a backpack would be 1 minus 0.06 or 0.94. So we're going to be using that as we find our answer. Okay, so and this, my little red stuff up here is just for one. We're looking at all 20. So we're going to say 0.94 times 0.94 times 0.94, and that would be for all 20, so on to 0.94. So I'm going to just rewrite this as 0.94 to the 20th power. And you can put this in Excel, and you should get 0.290. Okay, so again, this is saying all 20 iPads damaged in a way other than a bag or a backpack. So to find how many are damaged by a backpack, we will do our complement rule. So 1 minus the probability of the complement of A. So 1 minus 0.290, and that would give me 0.710. So the interpretation for the iPad damage problem. For a group of 20 damaged iPads, there is a 0.710 probability of getting at least one iPad damaged in a bag or backpack. This probability is high, but it is not significantly high. To be reasonably sure of getting at least one iPad damaged in a bag or a backpack, we would need more than 20 damaged iPads in a group. So remember, a larger N gives us better results. Here we're going to look at the intuitive approach for finding the probability of B given A. The conditional probability of B occurring given that A has occurred can be found by assuming that event A has occurred and then calculating the probability that event B will occur. So the formal approach for this is the probability of B given A can be found by dividing the probability of events A and B occurring by the probability of event A occurring. Here we're going to look at an example of pre-employment drug screening. And the first one says we're going to use the following table and find if one of the 555 test subjects is randomly selected. Find the probability that the subject had a positive test result, given that the subject actually uses drugs. So that means we're finding, and here you can see how it's written. So the probability, a positive test result given the person uses drugs. And then you can see your table there at the bottom. So again, we want the probability of a positive test result given the subject uses drugs. So we are assuming the selected subject actually uses drugs. So you're going to look at the top row, and that gives you, and I'm just going to give you a little sketch here. So our subject number, again, we're just looking at that top row. Positive result, negative result. So we have 45 and 5. Now remember, this is just a little snippet of that top row. So we have a total of 50 subjects that use drugs. And that's coming from this second part. So remember, it's a positive test result given the subject uses drugs. So because we're doing the given the subject uses drugs, we are just looking at that first row. And then looking at the 50 subjects that use drugs, how many of those had the positive test result? So 45. So we can write our answer as 45 over 50. So the subject uses drugs, that given is our denominator, and how many had the positive test results is our numerator. And if you simplify this would be 0.900. We can use the formal approach and get the same answer, and I'm going to show you just so you can see how to do that. So I'm going to bump this up so we have enough room to write. Remember the formal approach is the probability of B given A equals the probability of A and B over the probability of A. So just as a reminder, we are looking at the probability of a positive test result given they use drugs. So that means that the probability of A and B is that they have a positive test result and that they use drugs. So you're going to be looking at the total number of subjects, which is 555, and then how many are positive and use drugs? That's 45. 45 of the 555. And then your probability of A, and A is just the probability that they use drugs. And out of that, that would be the top row, so 50 out of the total 555. And then in Excel, you can enter this. Just be careful with parentheses here. You would want to make sure that you do parentheses around 45 over 555 and then parentheses around 50 over 555. You should get 0.900 as your same answer. So either way can give you the correct answer. I personally like the intuitive approach because it breaks it down a little bit and you can see what you're looking at from there. So by comparing the intuitive approach and the formal approach, it should be clear to you that the intuitive approach is much easier to use and is also less likely to result in errors because you're not trying to get so many different probabilities and put them together. We're going to look at another example. Use the table and find the following. If one of the 555 test subjects is randomly selected, find the probability that the subject actually uses drugs, given that he or she had a positive test result. So that means that we are finding the subject uses drugs given a positive test result. I am going to work this out on the next page, but I'm going to go ahead and let you see here. Because we're looking at given a positive test result, we're actually going to be looking at the column. Okay, so we've got 45 plus 25 gives me the 70, and how many of that 70 uses drugs? And that's where you get your 45. You're going to see some detailed explanation on the next slide, and then I'll have your answer for you. This is just explaining again that we only have the 70 subjects from the column of the table, and then we are looking at that to get our number that used drugs. So our solution is that among the 70 subjects, 45 used drugs, so we should have 45 over 70, or 0.643. So the first result of the probability a positive test result given a subject uses drugs was 0.9. And that indicates that a subject who uses drugs has a probability of 0.9, or a 90% chance of getting a positive test result. The second result of the probability a subject uses drugs given they got a positive test result is 0.643. And that is indicating that for a subject who gets a positive test result, there is about a 64.3% chance that this subject actually uses drugs. Now, I want you to notice that the probability of positive test result given subject uses drugs is not equal to the probability that a subject uses drugs given a positive test result. So in that prior example of the probability of a positive test result given a subject uses drugs is not equal to the probability a subject uses drugs given a positive test result, this example proves that in general that the probability of B given A is not equal to the probability of A given B. There could be individual cases where it is true, but they are generally not equal. And to incorrectly think that the probability of B given A and the probability of A given B are equal, or to incorrectly use one value in place of the other, is called the confusion of inverse. Let's consider these events. D is dark outside, and M, it is midnight. In the following, we conveniently ignore the Alaskan winter and other such anomalies. So here we have the probability it's dark given it's midnight. So remember, that means you're first looking at it's midnight, so therefore it is dark, and that probability would be 1. So again, it is certain to be dark outdoors if it is midnight. The next one is the probability it's midnight given it is dark. So that is saying the probability that it is exactly midnight given it's dark, and you have to think about, well, it's dark for a range of hours, right? So midnight is 1 minute out of all of the night. So that would mean it's almost 0. So here you can see that the probability of dark given midnight is not equal to the probability of midnight given it's dark. And confusion of the inverse occurs when we incorrectly switch those probability values or think that they are equal. We're going to look back at another example using the tables. So here we have assume cancer has a 1% prevalence rate, meaning that 1% of the population has cancer. Denoting the event of having cancer by C, we have the probability of cancer is 0.01 for a subject randomly selected from the population. This result is included with the following performance characteristics of the test for cancer. So the probability of cancer is 0.01. There is a 1% prevalence rate of cancer. The false positive rate is 10%, and the true positive rate is 80%. So you have to be careful here. False positive means a positive test given the cancer is not present, and a true positive will be a positive test result given that cancer is present. We are going to fill out the table on the following slide. So we are going to be filling out this table, and this is going to summarize the cancer presence and the test results for 1,000 randomly selected individuals. And this is a hypothetical situation. So we know that 1% are expected to have cancer. So we're going to look at this top row of have cancer. And to get this first row right here, this first little cell, I'm going to say 1% expect to have cancer. So 1% of the 1,000. So you're going to just do 0.01 times 1,000. And this is going to give me 10. My second thing is just to, since we know we have 1,000 subjects, we can do subtraction to get that next cell. So here, I can say 1,000 minus 10, and that gives me 990. Now, the problem told us that there is a 10% false positive rate. So that's looking here. And that means that among the 990 subjects without cancer, 10% get a positive test result. So we're going to do 990 times 0.10. And that's going to give you 99. So we have 99 here. The next thing I will look at is an easy piece, right? So now we can come here and we can say, well, if there's 990 and I've already pulled out 99 to get the false positive, you can do subtraction and you'll get 891. So this was my fourth thing I did. And you may not always go in this order. I'm going by things that I was told in the problem, and that's how I'm getting my answers. Now, the next thing we're going to do is we're going to look at, okay, well, I know from the problem that it said that 80% of subjects will get a positive test result. So we're saying 80% of the subjects, now this is going to be a true positive, right? So 80% of the 10 are going to get a true positive. So you're going to say 0.8 times 10, and that's going to give you 8. And then to get that last box right here, you're going to do 10 minus 8 and have 2. And then I always finish out with what are my totals down there. So let's go ahead and do that. So 8 plus 99 gives me 107. We may need this as we are answering questions. And 2 plus 8, 91 gives me 893. And so now we have all of our table filled in. We can now answer the question. And remember, I'm going to just bump this up so we have room now to answer. If I'm looking for the probability of cancer given a positive test result, then I can say, okay, they were given a positive test result, and that's going to give me that 107, okay? So remember, we are going to use that intuitive approach. So positive test result is going to give me that total of 107. So that's my denominator. And then of that 107, how many have cancer? And then if you look, so where I have that green box around, 8 of those have cancer. And we can put this as a decimal, so 0.0748. So again, we looked at the positive test results first, and then how many of that positive test result had cancer. We can now interpret our results. For the data given in this example, a randomly selected subject has a 1% chance of cancer. But for a randomly selected subject given a test with a positive result, the chance of cancer increases to 7.48%. So based on the data given in this example, a positive test result should not be devastating news because there's still a good chance that the test is wrong. Now, again, this was a hypothetical situation. I would hope that in real life, that if someone got a positive test result, it would be more correct. In this case, the chances did not go up very much, and you can see that here. It went from 1% chance to only a 7.48% chance. Prior and posterior probability. So a prior probability is an initial probability value originally obtained before any additional information is obtained, and a posterior probability is a probability value that has been revised by using additional information that is later obtained. Relative to the last example, the probability of having cancer being 0.01, which is a probability that randomly selected subject has cancer. It would be what we would say as a prior probability, and then using the additional information that the subject received a positive test result, and we found that the probability of cancer given the positive test result was 0.0748. That would be our posterior probability because it used additional information of the positive test result. So the definition of independence. This is just a reminder. So event A and event B are independent if the probability of B is equal to the probability of B given A. So that means that the probability of B does not change when we know that A has occurred. Then A and B are independent. If two events are not independent, we call them dependent. And here we're going to look at that again. So we had the probability of cancer is 0.01. The probability of cancer given the positive test result was 0.0748. And since the probability of cancer was not equal to the probability of cancer given a positive result, then cancer and positive results are dependent events. We saw a change in those probabilities. So the new information of a positive test result changes that probability that the subject has cancer. You should be able to now do your MyStatLab homework for 4.3 and finish out those lab manual pages that I told you at the end of 4.2. There is a mixture of 4.2 and 4.3 problems. And then we will be moving forward into Chapter 5 after you take your Unit 1 test. Again, if you have any questions, you can always go into our Microsoft Teams channel under Unit 2 questions, and I'm happy to answer anything there.